This course is an ode to the unreasonable effectiveness of mathematics in 15 stanzas. So every stanza starts with a strophe. Walk with me. You, the chorus, pedestrian chorus, you join me. You raise your voices. Epode, math takes over, takes you to mountaintops, and what you see is a glorious vista. So if I get any of that across to you, I've succeeded. This recording will serve another purpose. If you ever get lost in a course and ask yourself, why is Predrag talking about this? Please go back to this video, because for me, the whole stream of this course makes perfect sense. For you, it might look like a bunch of disjoint topics. So I'm trying to give you an overview. Why am I doing things that I'm doing in the sequence I'm doing? And we'll get into details in the next 15 weeks of the class. So what is our story? I'll start it as a physicist, even though this course is also for engineers, bio people, applied mathematicians, whoever else needs to learn some applied mathematics or mathematical methods. Heisenberg, on June 7, 1925, discovers the following thing. A quantum state phi at time t is a quantum state at time 0 evolved by quantum evolution operators I over h bar, a Planck constant, Hamiltonian operator t, where this Hamiltonian operator, and I don't expect you to know this, depends how you learn quantum mechanics. Some people learn it in a Heisenberg way, some learn it in Schrödinger way. They're both okay. But this is just motivational. I'll explain in a little detail later on. So Hamiltonian has a kinetic term and has a potential term. And this thing is called Hamiltonian operator. And what the hell is that? And Heisenberg says, voila, I've invented matrix quantum mechanics. It was born in 1925, who said, this is matrix. So if you ask what's operator, Born said, well, operator is a matrix. It's a very big matrix. And the next thing that happens in this story that I would like to wrap the course around is that Dirac, in 1939, says, I can solve this. If I use symmetries. So even though this is a huge matrix, if you know what symmetries are, you can solve this problem. I'll explain in the first week of the course in more detail what this is. And you say, well, I'm a neuroscientist. This is the third millennium, I don't care about H bar. That's not my problem. Those people are dead. And also, my matrices are much bigger than your matrices because I'm collecting brain data. I have huge matrices. So what are you going to teach me? And the theorist says, hold my beer. The only thing that's quantum mechanics in this here is h bar. That's just a unit. What I'll show you is that everything else of this mysterious stuff is just 19th century. So my role here is to demystify everything. Quantum mechanics is profoundly mysterious, but the only mystery is why h bar. All this other stuff is mechanics, which I'll teach you. That's what math methods course is supposed to teach you. A brief run through the course. Week 1. I'll teach you about matrix functions. And what is that? It's a way of starting with a number. Things that you know, like x or f of x. And replace it by array and show you that all of this works. The start is very easy. So for example, I'll teach you that exponential remember, Heisenberg says exponential of this operator does something, blah, blah, blah. So what is that? Well, exponential of the matrix, to understand what it is, you just need to know that matrices add and multiply. And then you know that exponential of a matrix A can be written as a series, Taylor series. You know what a Taylor series is. You add the terms and you raise them to the power, meaning multiply, and that's it. It's very easy to define them. And then, I promise you to show you something you don't know. Of course, you know all of this stuff because you know how to multiply matrices and why, etc. The big surprise of this week that in h bar quantum mechanics units, so I'm an atom, I'm not 1 meter big, this function that Heisenberg uses can be written as a matrix. And that matrix is a limit of lots of short steps. Short steps in time where I put in the potential part, the kinetic part, and it turns out these are just ordinary matrices, as you will see. And a very mysterious thing that some of you might have learned is that tells you that Heisenberg operator minus I h bar. Time ordered integral. And this is just classical. This is 19th century. Precedes quantum mechanics. Week 2. We'll learn about a German word again. Eigen, meaning myself, proper, etc. Eigenvalues. Now, what's an eigenvalue? This is the opposite of what I taught you first week. First week, I taught you if I understand something, a function of a number, to also understand a function of an array, so I can go to larger and larger objects. Eigenvalues are magic. Eigenvalues are magical because what they do is they take arrays of numbers and convert them into a number. So if you remember anything from this, I can take my matrix, let's say Hamiltonian or something, and I can subtract from it the eigenvalue, let's say energy. I divide it by difference of eigenvalues. For normalization purposes, doesn't matter. And I take a product of all j's not equal to I. And this thing converts operation of working with a huge matrix into just evaluating as a function of a single number. So that's called many things, but I'll teach you how this works. And once you know that, you can do things that are called normal modes. And this is very convenient. For example, if you have a spring matrix, you can find bouncing spring matrix. You can find out all its resonant frequencies. You hit it here and it does something. If you don't care about spring matrices, you can figure out vibrating modes of CO2 molecule. Now that's important. That's chemistry, and that tells you how you dissociate molecules, etc. But it only requires this trick of going from large matrices to numbers using method of eigenvalues. But then, big surprise, and 19th century guys didn't know this, you can do quantum mechanics. Actually, the way they teach you mechanics, they only teach you these eigenvalues, you never understand why. But this is just standard thing about matrices and large arrays, and quantum mechanics is almost nothing except the mysterious H bar. Or you might be a musician. You can figure out modes of a guitar string. So, much of what we do in music just requires this, both on a level of player and a level of encoding music, requires this technology. So you might be using it much more than you actually realize. We go to week 3. You happen to be a thoroughly modern person. Your problem is nonlinear. And I'm teaching you matrices. Everyone knows they're linear. So you're right. Sounds like nothing to do with matrices. I solved some differential equations. We'll do that. But then you have to ask yourself, how stable is my numerical solution? And what do you know? the same thing that I taught you previously as the, time order evolution operator, but now having to do with classical flow in a neighborhood of a trajectory. You have to compute matrix, you have to compute its eigenvalues. And it turns out, when you actually think this through and do it, you have discovered chaos. Now that's a pretty modern thing, and sometimes it's called turbulence, and etc. But to do it, you have to use matrices. So here we go back to old stuff. I taught you matrices, so you would like to learn about week 4. Just to get a hang of it, what about 2x2 matrices? Well, you pretty soon discover there is a special set of them that are called complex numbers. Euler discovered this in 18th century. Or, well, Hermite, Euler, and so on and so forth. Okay, you're familiar with complex numbers. I'll explain to you how you think of them as 2x2 matrices. And then magic happens. It's called Cauchy-Riemann, French-German thing. And it turns out that for those very special complex numbers, you can define derivatives which are one-dimensional. Which is very counterintuitive because matrices is 2x2, so you should be able to go into 2 directions. So, okay, maybe you're not so impressed, but we go to week 5, and we teach you something called Cauchy, counterintegral. And the magic there is that this integral on the contour means you integrate over a line in 2-dimensional space. The result doesn't depend. Same result for all contours. So that's a little bit magical. Okay, but you don't care because, you have more important things to do in your life. You are a working person. Why should you care about some magical contour in a complex space? And indeed, there are lots of magical things in mathematics that you don't care about, but Cauchy theorem at work is so amazing that we're very sad we don't have more than Cauchy theorem in other settings. It works for this 2-dimensional space called complex plane. And what it does for you, surprise, if you have problem written in real variables, it's really worth your money to just make them complex. So you go from real to complex. Seems like unnatural complexity. This is 1 number, this is 2 numbers. So why would I be doing that? Then you call in Monsieur Cauchy. And what does he do? He solves for you electromagnetism. For example, Dirac was trained as electrical engineer. That's why he could invent quantum mechanics the way we teach it today. So it solves quantum mechanical problems. If you are a fundamental kind of person, and this is child's play, it solves quantum field theory problems. We couldn't do quantum field theory without Cauchy. If you don't care about that, but you care about, materials, stuff, well, we can't do stat mech without it. And the list is endless. So it might seem like a diversion, but it's great stuff. So one thing that you do with using Cauchy, and that we do in week 7, we can put counters various places and do approximate integrals of things we cannot compute exactly. And that's called method of steepest descent. As always, we'll start in pedestrian way. I'll teach you or remind you how to do it for factorials or some silly thing like that. But the basic idea is that in when you have mechanical systems and you're close to the bottom of potential, all bottoms look parabolic, like parabolas. It just means that if you're at the bottom, something smooth and you don't care, do it very carefully, you can put some kind of circle there that is tangent to the bottom, and that's a good approximation. And then you have to compute that. Whenever we have a system like that, we can compute it analytically exactly, etc., thanks to something called Gaussian integrals, which I'll do later. But you have to compute corrections. They're called perturbative series. And might seem simple to you, but it turns out it's something very fancy, has a name. It's called Feynman integrals. And people can get tenure just computing Feynman integrals. It's a serious business. To this very day, if you check archives, it's full of Feynman integrals. And then I always promise you, this is all chorus, pedestrian stuff, etc., but I promise a surprise. The big surprise is that these corrections, and I've dreamed all my life I can come to class and I can explode something, but can't do it, it's online. But this series explodes. Something we do all the time, works very well, but actually, honestly, it's explosion. Right. Still, we do it because it's the best thing we know how to do. Now, this is all complex. We have been in complex plane for 4 weeks now, but let's go back to our original thing. Let's go back to matrices. And what we do now is we pose a problem that can be explained by multiplying things by matrices, but then we say this problem has a symmetry. Remember, Dirac could solve everything because he used symmetries. So we have to give a flavor of what's a symmetry. And discrete Fourier transform is the simplest example of that. It's an example of system, let's say, molecules connected by little springs, equal mass, da-da-da. So it's one of our normal system problems. But the symmetry is very simple. We can label these identical little balls in this way, or you can decide that 1 is this guy, 2, 3. So you can relabel anyway to 1, but it's a symmetry. It's the same physical problem. That's a simple example of symmetry. So now we'll learn that this is just a permutation. We write it in terms of matrices. Matrices will have 0 and 1s in them. Zeros and 1s because they're permutation. So either you multiply something to 1, you moved it, or you don't multiply 1, and that's all. But now we learned that we're supposed to look at eigenvalues whenever we have matrices. They are complex. They make no sense because we have a real object that's full now of complex numbers. But, you know, the two threads have come together of looking at matrices and looking at things in complex plane. But it turns out understanding this is an incredibly powerful method. And that we learn in week 9. When we go to continuous version of this, it's called Fourier transform. And you know what it is it's still matrices. But now transformations are not boom, boom, boom by finite amounts, they're infinitesimal. In other words, we have gone from discrete world of things on chains to continuous world. And, you know, it's not such a big deal. You're just running in circles. It's what electrical engineers do for a living. But it turns out this is a gateway drug. Because if you start understanding this, you start understanding nature's fundamental symmetries. So things like standard model of particle physics or superstrings, etc., they all have their origin in thinking in terms of discontinuous transformations. Now, we're not going to cover all of physics right here. So we will teach you something very simple, week 10, but it gives you flavor of the big things ahead for you. We'll teach you discrete symmetries. And again, this is 19th century. Tilings of space. And in 19th century, they led to crystallography. Which is amazing. And all of our condensed matter, like graphene, is based on these ideas. So lots of physics that we do in our building on various floors experimentally is based on this. But week 11, let's go continuous. Still, we're just thinking of matrices plus symmetries, but we'll do something you know very well. Rotations in 3 dimensions, that's called spatial orthogonal group in 3 dimensions, how you turn blocks in 3 dimensions. And something that you didn't ask to see, but we force you to see, special unitary group in 2 dimensions. So, who cares about that? And I know what rotation is about. What is this complex numbers in 2 dimensions? That's not physics. That's not my world. And here comes a big surprise that, leads to lots of deep thinking about nature of space and time in quantum mechanics. Your classical, space which has coordinates x, y, and z, you're in a corner of the room and x and y are on the floor and z is going up. This is actually a construct, and the fundamental building block is 2-dimensional spin. Now you would think they invented spin in 1924. Wrong. 81 years earlier, before quantum mechanics, Hamilton, a smart kid, at this time he wasn't a child anymore, in 1943, understood that our 3-dimensional space is best explained in terms of spin. So if that's not mysterious, I don't know, what you find mysterious. So this is, kind of things that theories get very happy. But again, you do real stuff. You're not here to learn stupid, fancy math, because you do experiment. You say, I don't need all this stuff. I'm a working physicist. I'm down in laboratory. I collect data. I don't need all this. All right. Week 13, we do start thinking about that. First, we have to do probability to understand the data. Surprise. I'll show you that Gaussians, these are distributions that you care, the same thing as harmonic oscillators. Now that's a little bit weird, but okay. Both are classical, so no big deal. One is noise, one is mechanical. But then they're the same thing as the Schrödinger equation. In other words, quantum mechanics equals noise. That's very weird, and we have to think about it a lot, actually. And I'm giving you a glimpse of one thing between what we have covered so far and what you're using when you're looking at your data. But, probabilities, that's still a little bit abstract. So week 14, I want to earn my salary. So I'm really teaching you what experimentalists do in the lab, which is math for experimentalists. So, surprise, or maybe not surprise, to do it well, good data analysis, turns out is good abstract mathematics. Much of it we covered in this stuff. All right. You still don't believe me because you are a neuroscientist. You are so 20th century as anybody could possibly be. these dead subjects like mathematics and physics and chemistry, blah, blah. But brain, that's the problem of our century, right? So what you have, you don't want to listen to us, but you have lots of data, neural record. Lots and lots and lots, because you might not like us, but we gave you transistors, we gave you computers, we gave you everything. So you can look at the brain. And it's lots of data. You have to do something called nonlinear or linear dimensionality reduction. And its matrices, they're rectangular. They're huge. They're not square. They're rectangular, and they compare apples to oranges because you measure something this way and measure, you stick electrode in brain. One axis is voltage, the other one is time. So they are weird things. Still, this huge rectangular matrices, sorry for my, I think you have to look at them. They're matrices. So what do? You either do principal component analysis or PCA, or you do singular value decomposition, SVD. You cannot understand either one of these unless you understood what eigenvalues were before. And if you want to go very nonlinear, you have to do something called isomap, which is, again, you have to take manifolds in a brain space, cover them by little linear charts. You cannot do this unless you understand matrices. So, surprise here. Matrices, or these arrays of data, get you deep into the brain. Now, this is going to be the last lecture. I might bring, an amazing brain scientist to do it. Whatever is mentioned in that lecture will not be on the final. And that's the course, and now we will start the real thing. Bye for tonight, or this morning, wherever you are. Ciao.
It's a beautiful course. It's rich. It's built beautifully. You bring some other sort of sense of history and some sense of continuity. I love that you sort of end most of the classes with a surprise. It's like a bonus and something. It's really beautiful. In other words, after this first class, if you have someone who is really curious, they got intrigued. They didn't understand anything and they got intrigued. And this is the main purpose of this class.